Hello, everybody, and welcome to the DATAcated show. Today, we are live streaming this show on LinkedIn, Facebook, YouTube, Twitter, and Twitch. And we have the pleasure of hosting TIBCO's special guests again with us today, Michael Okano and Neil Kanungo. They are joining us to talk about data analytics as it has to do with time and space. So I think it's a very, very exciting topic. This is going to be a session that's slightly different than what you might be used to, because I'm actually going to give them the stage in just a few minutes here, and they're going to take over. They've worked really hard on a presentation for you all today, so I'm really hoping that you get a lot of value out of this presentation. I'm personally really excited to learn all about data analytics and time and space and what TIBCO has to offer. Before I bring on our guest speakers, I want to let you know that we have a fun giveaway today. The way to play is, I'm going to share my screen here, is using a hashtag TIBCO in the comments. So if you're joining us on YouTube, Twitter, Facebook, LinkedIn, or any of the other platforms that we're streaming on, all you have to do is type in hashtag TIBCO and participate in a raffle. Now, you have a chance to win the membership for the DATAcated Circle, which is a $300 value, and it gives you access to monthly live shows with experts that are for members only, as well as about 10 data courses, one of which was authored by Neil Kanungo. And once he joins, I'll ask him to talk a little bit about the course, but it's essentially on how to go from data to dashboard with TIBCO Spotfire. All right, I'm going to stop my screen share here, and I'm going to go ahead and bring on our guests. We have Michael and Neil here. Hello, guys. How are you?
Hey, Kate, how are you?
Hey, Kate. Hey, Neil.
Hey,
Michael. Good morning.
Great to see you both back on the DATAcated show. I know you did a DATAcated takeover probably a couple months ago, but great to see you on the show here. And before I hop off, I just want to let people know that they can ask questions. We will take their comments, and I will be popping in and out of the show. Hopefully not interrupting, but we're going to take as many questions as we can throughout the session as well. So as Michael and Neil are talking to you about time and space, definitely feel free to jump into the comments. I'll also be there sort of backstage answering some of the comments. Neil, anything you want to say about the course before I hop off?
Yeah, no, we have a great course on Kate's DATAcated platform. It's data from story to dashboard, or from data to dashboard, and it is using Kate's actual YouTube data, and we use it in TIBCO Spotfire. TIBCO Spotfire is something we're going to be showing a bit of today. It's our visual analytics product, and it's really intuitive, easy to use. You just kind of drop your data in, and you can drag and drop, create your visualizations, you can create interactivity automatically. So it's a cool course, and yeah, go ahead and enter in hashtag TIBCO, get access to that course as well as the full platform. So
all right, awesome. I'm gonna hop off. Have a good show, guys. I'll see you in a few minutes as questions come in.
Thanks, Kate.
Thanks, Kate.
Okay, so let's get started. Visual analytics in space and time. I'm Michael, and have Neil with me, and we're going to go through firstly visual analytics principles in general. We're going to then get into time, the fourth dimension, into space, the final frontier, and then wrap it up with the space-time continuum. So 4 sections in the talk today. So let's get it started, Neil. Let's start talking about visual analytics principles: perception, estimation, inference, and insights. And the way this works, the goal of the author is to get the viewer to perceive data patterns. And you've got to make it accurate and fast. The speed of cognition is important. You know, the human brain can process entire images that the eyes see in as little as 13 milliseconds. That's from an MIT study on the slide here. And so you want to take advantage of that. You want to quickly, get the message into the other person's brain. And detection is important. First step of that, to recognize the geometry encodings of the values on the visual. And then assembly is the next part of the brain process, grouping graphics, the symbol elements to construct the patterns. And then estimation, estimation and assessment of the relative magnitudes on the visual displays of the metrics that you want to get out to the viewer. So that both accuracy and speed are important. We're going to start off with some time of the week patterns here. And this is electric power usage going on the left-hand side from Friday morning into Saturday and into Sunday. So different power usage as a function of time of the week here. So let's see, maybe you can guess what sorts of buildings these are. But the one across the top there, these are, every day. They've got a pretty similar pattern. So this is like a business, that runs every day of the week. Now, the next one down on the left-hand side is a little bit different, in terms of the Saturday and Sunday, right? So there's not so much going on in the morning. And this is a restaurant and a nightclub. That's the type of diurnal pattern that those usage of electricity that those sorts of buildings have. The next one looks pretty consistent, right throughout. So that's like a single family home. The next one on the top of the second column, this looks like something's broken. And in fact, these are broken meters. The next one really fades off over the weekend, right? So this is really a downtown business that, is operational on Friday, but fades off, on the weekend. And then finally, this sporadic pattern on the lower right is a set of condos. So you can see these patterns in time in this case for different electricity usage as a function of time of the week. That's a quick example. You want to jump in, Neil?
Yeah, I was just saying, I like how there's you can see all the different signals right there in gray, but that red line helps with the estimation part. So when you spoke earlier about estimation, you can estimate the overall trend, and that helps with the speed and accuracy of the interpretation.
Absolutely. And we've got a number of examples about techniques about how we draw out that shape for the estimation and for the inference. So let's step through estimation, inference, and the rest quickly here. So the way the humans compare estimate things from graphs. Humans are not that great at estimating differences on graphs. They're good at estimating differences in lines, but not when the lines get too steep. Humans don't naturally order color hues, so a limited number of hues can be discriminated. There's certain colors that set off emotion, so red is emotional and may be perceived as a larger space than other colors. When you do shading, larger regions can appear darker. So you've got to kind of be aware of how humans are able to estimate differences on graphs. Now, Weber's law says that the probability of a human detecting a difference in two lines is related to the ratio of the line lengths. So grid lines, soft grid lines can help. Sorting by order of categorical values can be helpful. And in scatter plots, getting the aspect ratio so that the average of the slopes you're trying to discern is about 45 degrees can be helpful. So let's step through some of these concepts and understand how inference is drawn from the way we display data. So as I mentioned, the order there of perception abilities from very precise on the top chart on the right-hand side, positioned on a common scale where the length shows a greater value is the most accurate on the top there. Position along identical non-aligned scales is also a reasonable way to do things. Length, as we showed, is a good one. We're very good at with the eye of looking at comparing different lengths. Angle and slope, somewhat, but then below the line on the left-hand side, area, volume, color hue, we're just not very good at doing that. So as you sort of step down the chart, on the right-hand side, you can see on that third one down, the width is greater on that third line, but you can't tell by how much greater. And then the size, bigger is greater on the next one down. You can see that one's bigger, but you can't really tell like the relative magnitude of how much bigger. And the same, with respect to the intensity. So you got to be, cognizant of that and use those human perception abilities to get the reader very quickly to estimate what's going on with the display that you create. So Neil, let's get into a couple of examples of that with length and color.
Hey, Michael, just a quick question. It actually is relevant to color and color hues. Is there sort of a ballpark number that you recommend that people sort of don't go over a threshold of using too many color hues?
Yeah, let's show the next slide. I think we're going to get into a little bit of that.
Okay.
Yeah. Yeah, so I use a ballpark number of around 5 or 6. Once it starts to get past 5 or 6, then you're starting to get to really close to other colors on the color wheel. So your color wheel kind of be 360 degrees. You can divide that into 6 equal slices, and you're getting good spaces around that. Now, these are not color wheels. These are pie charts. But what this is demonstrating is the value of showing length and the accuracy of the inference and your perception when you look at length. So at the top, those 3 pie charts all look like they are identical. But below those pie charts are these bar charts. And these bar charts are actually the same data that's used in the pie chart above them. So you can see in the bar charts, because we're using length, that the data is actually different. You can see kind of an increasing trend here. You can see a kind of varied trend here and a decreasing trend here. So these categories, it's not an actual trend, but these categories are different values that you wouldn't be able to perceive with angles and slopes, but you can perceive with length. Let me move forward here. So another concept with angle and slope is banking at 45 degrees. When you have your data that is maybe if it's spread too wide, your eyes aren't going to perceive the differences in that angle and the data points. So for instance, these yellow points look like they're pretty far out. You can't really tell how much below the general trend of all of the data points that these yellow are. But when you bank that 45 degrees, you're getting a more accurate representation of those yellow points. You can see that they're much below where the pink and the blue points are. So banking at 45 degrees is a good visual practice when you're using slopes. Your eyes are able to perceive that, and compared to that, a lot easier than if you were to use something at like 20 degrees, for instance, which would create a really wide plot.
Yeah, so bottom line, use 5 or less colors or so. Use bar charts if you want to show height versus pie charts. And then if you've got lines, bank them so that you can, the average is 45 degrees. You can discern a lot of difference from that, but not at these flat or steep angles. So just a few basic tips on how to use color, how to use bar charts versus pie charts, and how to arrange your line charts. Now, what about scales, Neil?
Right. Yeah. This very first one is position along a common scale. So we have an example here. This is looking at COVID-19 cases and vaccinations worldwide. And there are obviously very different population sizes in different countries. And so if we are able to use a common scale, we're actually able to compare the relative size of these epidemic curves and vaccination curves by using a common scale. So at first it might look like, okay, this is all a little low. There's a lot of empty space here, but this space is actually being used by using a common scale. We can see, okay, here's the United States. We can move over to the United Kingdom. We can move over to Brazil. And so we're able to see these cases per 100,000 and the vaccination rate, which is also a proportion of the total population. So that common scale is easier to inference.
Yeah, absolutely. And then on the left-hand graph, we're fitting a smooth curve, just like we did through the electricity usage data in the first example. And that smooth curve allows you to really get the signal out of compared to the noise. So if you jumped onto one of the other more noisy ones there, Neil, I think it was Germany or Italy, maybe, where there's a lot of noise on the graph. Even that one, yeah.
There we go, Germany.
Yeah, Germany. So yeah, the reporting in Germany is like, less on the weekends, it looks like. So fitting a smooth curve through that is pretty important. Now we're going to talk a little bit about how that smooth curve was constructed later on. But, a lot of the papers like New York Times and so on are using 7-day averages. We've using Friedman's SuperSmoother curve, which seems to get better signal, out of the noisy data. But we'll bring that up a little bit later, Neil. How about telling a little bit more about the color scheme guidance question that came up earlier?
Yeah, related to kind of Kate's question on color schemes, there's and what type of colors to use. There are four standard color schemes, 4 types. There's binary, where you might have 2 categories. It could be true, false. It could be yes, no. It could be Democrat, Republican. There's 2 different categories. Below that, you have diverging, where you have two extremes. So it could be the degree of like Democrat votes versus the degree of Republican votes. So on one side and then the other side. So you have a continuous scale there. Now, sequential is numerical, but it goes from a minimum to a maximum value. It goes, it just steps up in direction, steps sequentially. And then qualitative has no order at all. And that is for like categorical values. And I say that can be like ice cream, it can be vanilla, chocolate, strawberry, it can be popcorn flavors or some different category that has no ordering to it at all. And the way that we can see that used, this is the same data across 4 different maps. And this is on honeybee production. And in the top left, you're seeing the colony yield of each honeybee colony, and that's above and below an average. So the green is above an average, the gold over there, that honey color, is below average, and that is a binary thing. So we took that data and we made it a very binary, true, false, above or below average. We can do that in a diverging format, which is a degree of it. So which one's the most over average? Looks like North Dakota there and Louisiana. And which one's the most below average? Looks like Maine over here, maybe Virginia. And then on the right here, this is sequential. So which colonies are producing the most? And this is just going in one direction. So you have North Dakota there, and you have lighter colors for Maine and Virginia, the states that are not producing as much honey. And then lastly, this isn't using the actual colony yield. It's just a qualitative thing. And this is just showing regions of the US. So there's no particular order here. You just have the West, you have the East, you have Central. That's how the qualitative color theme can be used.
Hey,
Right.
Neil, I think this is going really well so far, and people are loving the slide, especially this slide. Right before this, there was actually a question on, where you showed, that one, the color scheme guidance.
Sure.
Question came in here: are all of these colorblind friendly? And maybe you can talk a little bit about accessibility and.
No, that's an important point. Red, green color blindness or blue, yellow color blindness, can be an issue. So we do watch out for, combinations of colors that are, in that realm. But Neil, do you have any tricks to?
Yeah, we have a good slide on color blindness, didn't include it in this deck. This image in particular is not colorblind friendly, but that is something that you want to pay attention to. I mean, up to 6% of men have trouble with red-green color blindness or blue-green combination, one of the two. So that's when you are presenting dashboards to big audiences, that can be quite a big number. If you have 100 people looking at your dashboard, that's up to at least 6 people that would have trouble seeing that, right?
Yeah, and I think there's a site called Color Brewer 2 where you can actually select color blindness and then find the color scheme. Also some sites that can show you what it would look like to a person that suffers from color vision deficiency. And I'll put the links to those sites in the comments, but I'm gonna hop back off and let you guys continue. Thanks.
Yeah, thanks, Kate. No, it was an excellent point.
Absolutely. Yeah, thanks for bringing that up. Yeah, we've got a bit of a compressed and set of guidances today, given the breadth of the time and space topics. But thanks for pointing that out, and we definitely do pay attention to that. So we've talked about estimation and inference. Now, in terms of insights, we're very much in the school of Spotfire was invented at the Human Computer Interaction Lab with some input from Ben Schneiderman. And we really kind of adhere, at high level at least, to the visual analytics mantra that Ben put out all those years ago, with 3 levels of understanding: an overview of all the data, filter, zoom, and mark to an area of interest, and then get the details on demand from that filter, mark, zoom type of approach. So Neil's running a little video here that shows how, we've got a part of New York City. We sort of filter in or zoom in to an area of interest. We grab those particular people or homes that are in that region, and then we're able to dig into the details. You can see some of the details on the tooltip there. But that idea of overview, filter, mark, zoom, and details is really hits to that speed and accuracy goal of human, wanting to get to the nugget. And it's important, again, to reinforce the speed and accuracy to build speed to the initial important information overview, and then drill into the area that that you're interested in. So we're going to now use that just as a really basic sort of intro here, and then get into now time, and then follow that by getting into space. So in time, the fourth dimension, you have basic principles, time varying displays, event stream analytics, and applications. So in terms of basic principles, firstly, there's granularity considerations, right? You might have data coming through at, sub-second intervals, but you might really only want to be interested in making inference at every minute or every second. So understanding the time granularity and what is where's the information in the data, and how, what time scale do you want to show the data at? There's some tricks around how you can do that by looking at the autocorrelation, or the correlation between lags of a time series. And you can see, I'm going to get into an example here of the parallelogram where, across the top there, you've got, this is accelerometer data. So you've got X, Y, and Z position data from this device. And you can look at the correlation in time lags between each of the X position across the top row, the Y position next, and the Z position. You can see the correlation of the subsequent point to the current point. And you can use that to decide what granularity you want to show the data. Now, the other consideration in showing the data, granularity, is in terms of actionable time. How quickly can you actually respond to what you're seeing? So that can be a consideration in the granularity that you choose. And then there's the way that you aggregate the data on that granularity, median or mean or time-weighted average, the smoother estimate we've shown a little taste of. And then the different channels of data might want to be aligned in a common granularity in some cases. But let's take a look at the accelerometer data in a little more detail here. Now, someone, before we run the video, Neil, this is someone with an accelerometer on their belt buckle. And the first column is jogging. The first row is the X position. The next row is the Y position. Third row is the Z position. First column is jogging. Second column is walking. And third column is standing still. So you can immediately see there's a lot of jumping around on the jogging one on the left. There's not so much on the walking, and then not much activity on the standing. So let's run the video, and we'll look at the parallelogram analysis and decide, what granularity you want to analyze the data on. So we can see this accelerometer is getting like 1,000 hertz, like 1,000 readings per second is what's the default coming off of it. So I can look at the parallelogram, or correlation versus lag, on the right-hand side for the X, Y, and Z position. I can see that jogging, there's not a huge amount of correlation, but when you get to walking, there's quite a high correlation. And when you get to standing still, there's a super amount of correlation between the lags. So you can decide to sample the points, based on just based on that. So if we're going to start at 1,000 hertz coming off the piece of equipment, if we sample every 50th, we reduce it down to 20 hertz, which seems reasonable in this case. And then we make a prediction, I think in this case, we're doing about 10 predictions per second that we decided was a reasonable granularity that summarizes the data based on the internal correlation and gives us the inference that we want that's useful to us. So you can see that we're coloring the X, Y, and Z axes along the bottom there with respect to the state that the person is in. They're either jogging, walking, or standing still. And those have got 3 different colors associated with them. And you can see how we've summarized the data down in the top right-hand corner to make these 128 predictions across the X, Y, and Z variables that give us the prediction. The predictions there are whether the person is walking, running, walking, standing, or jogging. So we're able to, we did this as a live demo where someone was walking around on stage with the accelerometer on their belt, and we could predict whether they were walking, running, or jogging, versus the data we're getting directly off the accelerometer. But there's a couple of tricks and tips in there to just allow you to summarize, aggregate down the data to some meaningful level of granularity where you can get the summary inference from it. In this case, we're predicting whether they're running, jogging, or walking. But we showed you earlier on the COVID data where that is very noisy based on the reporting that's happening in different countries. And so the idea of fitting, a curve through this to summarize this time-based progression of cases in Germany, in this case, where you can see the really big differences in reporting from weekdays to weekends. So how do we kind of make sense of what's going on in Germany, say, versus other countries? And that's where the SuperSmoother comes in versus the moving average. So Neil, do you want to walk us through the bits and pieces, the comparison, I guess, of the moving average versus the SuperSmoother?
Yeah, definitely. Yeah, we've seen, based on different geographic regions, different countries, different states, you get different reporting cadences. Florida will report like once per week now. Some other states have moved to reporting once per week. And what that does is create a distortion in the perception of how many cases there are and what the data is. For instance, this looks pretty high, right? This looks like there's 45,000 to 50,000 cases on these days in Germany. But because there weren't cases reported on the previous days before, or there weren't as many cases, locations reporting to the overall data, you actually are getting a combined data here. So we want to actually smooth this out and average this out. So one way that's done, and we've seen very often, is a moving average. And so the moving average works pretty well. You can see that it's brought down this curve. It's actually shown us, okay, across a 7-day moving average, the epidemic curve is in blue. You have a little bit of a dip here. You have a little bit of a spike there, generally kind of moving up and down. But the problem with the moving average is that it's going to give you a lag that's half the interval of your moving average. So if your moving average is 7 days, you're going to have a 3.5-day lag. And that's what you're seeing over here, 3.5-day lag that this is actually shifted over. The other thing is that it doesn't do a great job at really recognizing a full bivariate interval. It's only looking at a fixed interval in a fixed sliding window, whereas a true SuperSmoother, which we're showing here in white, will actually do a bivariate prediction and look at different intervals. And because it's looking at different intervals for every point on the left and right side of every point, you're actually getting a nice smooth curve here. And so while that moving average is showing this peak here, that is actually probably more likely this blue is actually a reporting artifact, whereas this white curve is nice and smooth and it levels out that data. And this helps with your estimation. So, the topic of estimation and visual perception that we discussed earlier, we talked about it with the big scales. We talked about it with the electric grid data. This helps you estimate what is actually happening. Another example is the United States, where we saw this in the last fall of 2021. You saw these, fall of 2020 into spring of 2021. You saw these different spikes here. This drop is around Christmas and Thanksgiving. Now, that's not actually that the cases were lower on Christmas and Thanksgiving. It's that reporting institutions were closed and they weren't reporting. And so our SuperSmoother actually saw right through that and gave us a better curve. It didn't just drop down like that.
Awesome.
Yeah, the SuperSmoother does lots of smoothing. It does a little local linear, and then it does adaptive bandwidths, and then it smooths the residuals. There are multiple smoothing components to it that give that faithful representation of the trend in the data.
Yeah, this is really great stuff. We have a few comments, questions, and I also want to do our first giveaway at this point. So just a quick reminder for folks, it's hashtag TIBCO to participate in the giveaway. But the comments and questions are actually related to the SuperSmoother here. So first, people love the overlay. People love the use of colors in the presentation. And Dustin has a question here. He's asking if you can explain how the SuperSmoother was derived.
Yeah, it's kind of complicated, but it's based on a local linear regression with adaptive bandwidths. So the idea is to estimate a number of fixed bandwidth smooths with local linear regression, and then you leave one out, cross-validation from each of those initial estimates, and then you smooth those with a constant bandwidth. And then you go back around one more time, based on the smooth residuals, you get the best bandwidths from the initial estimates at each data point over the range of the predictor variable. And then you use those local bandwidths to smooth at a constant bandwidth, and you put those two estimates together and smooth you get the best bandwidths at the smooth levels that you've seen, and then the smoothed outcomes are then local linear interpolated. And then those interpolated points are then smoothed again, resulting in the final estimate. So the SuperSmoother refers to the number of iterations that you have in the smoothing process and going back and forth to the residuals.
Can you tell that Michael has a PhD?
No, this is Jerry Friedman. This has nothing to do with me. This is Jerry Friedman from Stanford. Produced this. He's he's the leader in non-parametric regression smoothing, and he came up with this method that just really took off because of it just really captures the the middle of the distribution in a nice way.
I thought your answer was going to be something like, we use TIBCO Spotfire. We click the button there.
Well, we did do that too, but we used the we use Friedman's R package to invoke this, and it's good. It's a good point because you can run any R or Python piece of code inside of Spotfire. There's a inbuilt Python and R engine in the product. Also in the cloud version of the product, there's an inbuilt service for running Python and R code. And one of the big differentiators of this product actually is that you can make an arbitrary marking on any graph or chart or map, and you can invoke an R or a Python script from that. Oh, wow. So yeah, we can just put a SuperSmoother on anything in the click of a button in Spotfire.
Okay, I love it. We can put it on anything, just like ketchup. Awesome. Or syrup. Hold on, I think the quote was syrup from the movie.
I don't like ketchup that much. Maybe on bacon.
Oh my God. So I'm going to go ahead and share my screen quickly here. We're going to do our first giveaway. So thanks for those who typed in #TIBCO. If you do not win right now, we're going to do this again towards the end of the session. So good luck, everybody. Have fun. And #TIBCO is the way to play if you're just joining us now. We are giving away a membership. Oh, congratulations to Kendall Ruber. I'll just jot your name down quickly, and we will follow up with you after the session to make sure you get your prize. Thank you so much for playing. I'm going to hop off the stage here again, and I'll see you guys soon.
Terrific. So Neil, that's a great example there on the SuperSmoother. Let's get into some time varying displays with line charts and other types of representations.
Yeah. I just want to mention real quickly before we move on, if anyone's interested in learning more about this SuperSmoother and how to use it, if you can go to our Spotfire YouTube channel, you just look for the TIBCO Spotfire channel. There is a video on how to use a SuperSmoother and how to use a low S function, how to use different smoothers. And while there's a lot that's going on under the hood, it really is an easy click of the button to just deploy these smoothers and use that in the product. But the video goes over both the one-click deployment of using the script, but also just the math behind it and how it's all working. So check out that video on our YouTube if you're interested.
Yeah, and it's super fast, the SuperSmoother. I mean, it's been tuned to be, really quick. I mean, I know there's a lot of steps involved there, but it's all just, local linear single pass type algorithms that are stitched together. But let's get into some of the time varying displays, Neil, and walk us through the, line chart to start with. That's the most common.
Yeah, so from kind of an academic perspective, we just wanted to discuss basic time varying displays, the different ways you can represent time on your display. So the quintessential example is a line chart. This is probably the most commonly used type of time varying display. And it's really good for continuous timelines where you want to see the magnitude change. You want to see historical trends. It can also be used for forecasted values. So this is the most common type of time varying display. Typically, you'll see the x-axis and the horizontal axis. You'll see that representing time as time progresses from left to right. And then you'll see some metric on the y-axis that's being measured. So that's
and that's the go-to. Like say, for example, the AI engine that we have in Spotfire, when you click around, if your time variable comes up in your in the automated suggestion, we automatically put it on the x-axis, and if you've chosen a continuous variable, we automatically generate a display like this. Having x-axis time, y-axis continuous, and putting a line. This is the most common time varying display, and it's our go-to when we're recommending with the AI engine.
Yeah, and it's a very similar type of line chart as a bump chart. Now, a bump chart looks like a line chart, but it's different in that it's showing relative ranks. So this is showing just some cryptocurrencies over 2020, and you're seeing how you have a Bitcoin and Ethereum kind of at the top, and you see Ripple kind of at the top and coming down. You see some new coins coming in, DOT over here. So this is very similar to a line chart, but this simplifies a view of many different series. This could be a lot harder to see if you had many continuous lines, like from our line chart that we showed before. So we have 20 different lines here. if I showed 20 different lines on this chart, it would all run together, be a lot harder to follow and to trace. But it's not as good for analyzing relative magnitudes, because you're just showing relative rank between the two, or between each category. You're not going to see how much greater is that Bitcoin market cap to Ethereum market cap, how much greater is that Bitcoin market cap to the Dogecoin market cap, etc. So that is the bump chart. And then the Gantt chart. Now, Gantt chart is used for discrete timelines. In the past, we were looking at continuous timelines, but this is really useful for project management. It shows the duration of a task. It shows dependencies of a task. What you have is your time going from left to right, and you have different tasks that kind of waterfall down. So you can see an overlap between this effort estimation, this MVP definition of the conceptual phase of this Gantt chart, of this project that's underway. You can also find dependencies where the groundwork must be completed, then the effort estimation MVP definition can be done. So we're seeing these discrete timelines, we're seeing overlaps, we're seeing dependencies all in one chart.
Awesome. And now going back to the SuperSmoother, I know we do love this chart, but one thing you can do with the SuperSmoother is to get a derivative off the end of it. So you can say, what is the velocity of a curve? And so you see on the top row there is one of the COVID SuperSmoother curves. And the bottom row there, we've used the SuperSmoother estimates to get a first derivative to show the velocity. So you can see how the velocity is sort of going up as we go up that first peak in the middle, and then it goes up in the second peak, there, and it comes back down and goes up again. But having that velocity is really good, because you can look at growth rates. Say, for example, with COVID in different regions, you can look at the trend, and we use that to highlight, what countries or states are trending up or down. And the SuperSmoother gives you that stability of the curve to be able to make estimates like that to get current trends or growth rates.
I think this is really useful. Just jumping in here, like when it starts to kind of plateau, it's hard to tell, is that rate increasing? Is it decreasing? Has it actually plateaued yet? So the velocity chart is a much easier way to read that, is above or below that line. And then when we're looking at waves, right? So we have that fall wave of 2020, and then we had a wave of the Delta variant that was last summer. Which wave was growing faster? Was the wave growing faster that was in the fall, or was the Delta variant growing faster, or is the Omicron growing faster? You can see that a lot easier when you look at a velocity chart.
Yeah, absolutely. Across time, and also across different regions that were trending in different ways at different points in time. Now, another way to look at time varying displays in, say, the stock market, for example, is a candlestick chart. Now, in this case, we're showing the range of data over different time intervals. In this case, I think it's daily data. The body of the box plot is the price range between open and close. The whiskers on the box plot show the high and low during the day. The bar chart along the x-axis shows the volume of stock traded. And then the color is showing if you're trending up in blue or down in red. So really interesting use of multiple aspects of this chart to show a lot of different information based on the box, the whiskers, the bar chart along the bottom, the color. So that's a good one when you've got daily varying data that's jumping around the place. Now, another one when you're doing time varying displays is to create an animation. And in this case, we draw upon the great Hans Rosling Gapminder analysis. In this case, we're showing again COVID cases where time on the x-axis, time is actually represented by the faint date in the background of the chart, right in the middle of the chart. So it's not on the axis this time; it's right on that background. And this is useful for showing relative changes, seeing a story of how data emerge over time. And so we kind of, we're sort of replaying the data in a time sequence that is static in this case to show a time trend. So let's run the video, Neil. And I think we've now got this for most of the length of the pandemic. We're starting actually at the beginning of January 2021. You can see in the background there. And in this case, we've got the United States. And the x-axis here is, number of cases per 100,000. And the y-axis is
that was the beta B1 variant that went right there. We saw Michigan.
Oh, the Michigan jumped out, yeah. And then the y-axis is the amount of vaccination. So you can see a big spread in the y-axis in terms of vaccination percentage, and then the x-axis showing the cases. And now we're into looks like October of 2021, and we're back on the left-hand side. Looks like not too many cases, but now as we get into December, we see everything charging across the right. So this is Omicron moving, and we can see the different states. And now we land sort of towards the end of January. And yeah, we're in that. Some states are still getting pretty high case counts on the right-hand side, and the velocity is the color. So red is a higher velocity than blue, and the size of the bubble is the number of people vaccinated. So a lot of information again being communicated with the time sequence in the background, and the different states showing their relationship between vaccination percentage on the y-axis and number of case counts on the x-axis. Now, this is on our TIBCO website, tibco.com/COVID-19, and across the top, you can see you can change the axes, as well. So highly configurable plot where, again, size of point, color, and the two variables, in this case, time is in the background moving with respect to the date that's showing up right on the canvas.
I just had to highlight a comment we had from our audience. Mike said he liked our velocity calculation earlier. He said it's more like the super duper smoother. So that might be a good new name for it. Thanks, Mike. The super duper smoother on our velocity.
Yeah, that's funny. Good one, Mike. Yeah, but yeah, being able to do derived calculations like the velocity is really useful actually, because we arrange on our COVID dashboard, different states and countries with respect to the velocity of trending. So, any case, this time varying display in this case. Time is not even on an axis, but it's governing the animation, and you can see going from beginning of last year how most states were getting vaccinated, not too many cases, but then you see when Delta started to hit in the middle of the year, you see some states zooming across to the right as their case count jumps up. You can see I think Florida and Michigan and others, and then so Delta kind of died down there, I guess. Around August or so, or in September, I guess. And then, towards the end of the year, we thought we were done, but towards the end of the year, Omicron showed up, and you can see a bunch of the states moving to the right with increased case counts. And you see the spread on the y-axis with respect to different percentages of vaccinated people in the different states. So a lot of information being communicated on that graph, and hats off to Hans Rosling, who invented this. We call it the animated bubble chart in Spotfire, but it was really Hans Rosling's original work on Gapminder.
I like trying to interpret the vaccine efficacy. So when we saw the Delta variant and we see this wave here, so lower on that y-axis are least vaccinated states, higher on the y-axis is more vaccinated states, and then the cases are shown on the x-axis. So when that Delta variant hit, it hit some of the least vaccinated states a little bit harder, whereas the more vaccinated states had a little blip, but not quite as high as a blip. And
exactly.
And then Omicron, we know, has had a lot of breakthrough infections, and we're seeing that hit everywhere.
Yeah. Good point, Neil. So another way of doing time varying displays is forecasting. And again, these are pretty much all these built-in methods into our software, Spotfire. But this is a Holt-Winters analysis where there's three components in a Holt-Winters forecast. It's a non-parametric analysis. It's forecasting from the history of the time data. There's no other variable being used, just the sequence of the time measurement. In this case, we've got an example where we're looking at demand of coffee sales on the y-axis on the top chart versus time on the x-axis, and we're forecasting out into the future. Those projections there are based on the patterns that we've seen in the past. So the three parameters are the level of the actual data, the trend in the data, and the seasonality, which is the pattern that in the historical part of the data. There's two variations on the Holt-Winters. There's an additive with a seasonal component and a multiplicative where the seasonal component actually changes versus being constant. And let's run the video, Neil, on the next slide to just show the demand of coffee beans in the Bay Area as a function of time. And we're basically changing the number of points in the future that we're forecasting there on the slider. And you can see how the forecasts are picking up the pattern of the data in the previous months. both the seasonal pattern as well as the level and the trend. Okay, there's lots of other ways of doing this time series forecasting. We're kind of giving a bit of a whirlwind tour here. But let's get to the next important topic, which is, okay, we're actually now getting event stream data in this. We're going to walk you through. In the past, up until this point, we've just shown historical time data. We've replayed it on the animated bubble chart. We've forecasted from it on the forecasting piece. But now we're going to show you when you've got data actually coming in as event data are arriving. And along the bottom there, you can see how we are able to process that by cleaning the data, building up features. You might calculate slopes on a sliding window. There's a lot of things we do on time varying data. This is kind of a strength of TIBCO. And you can see, on the chart on the top right, there's those curves are moving in time as we pick up new data coming, in this case, off the equipment. And we're doing like calculations of slope, or we're just basically presenting the new data. And this is an event stream calculation versus a static data that we've had in the past, previous slides. So Neil, do you want to walk us through how we can build up a real-time event stream analysis?
Yeah, and I just saw this question from Petri about how about predictive and prescriptive stuff. So we're actually now about to start moving into the predictive and prescriptive stuff. First, we're going to talk about, as Michael said, the event stream calculations and just event stream. So this is not just data that is being replayed that's at rest. It's actually being collected in real time, and it can go through a actual predictive model. It can go through predictive calculations. But first, we're going to just talk about, let's just look at some displays. Let's look at what real-time displays are. So probably the most basic one is just a table, right? So the table visualization, very similar to how you would have an at-rest table visualization, where you show you have a lot of detailed measurements available. But this table doesn't have any like historical context available. You're seeing these numbers change. Now that's aided by the interpretation is aided by the colors changing on this actual table, but it's only showing instantaneous values. Now, if we want to start seeing some historical trends, we want to start seeing the general pattern of these values. And what I'm showing here are actually equipment wells. These are wells, fictional wells across like the Texas region in the energy industry. And this is showing certain measurements on pressure and temperature on pressure and current, on submersible pumps. So we're seeing the instantaneous measurement there. But if I want to see the trends on each of these wells, a line chart will be better. We talked about this earlier, how you get a continuous representation, highly interpretable trends. You're getting both the context of the history as well as the instantaneous value shown in this chart. Now, a map chart can be used. In this example, it's showing instantaneous values as well. And that's emphasized by color and shape and size. So we can see when a well is starting to perform poorly, then you have some equipment is sending us an alert. We're seeing these red dots actually jump here. And these green dots change from yellow to red. So that geographic context of the latitude and longitude is further emphasized by the size, the shape, the color. There's no historical context given here. Another example of a real-time display is a rose chart. Now, this is easy to interpret instantaneous outliers in magnitude. So you're not getting historical context, but here we have one of the wells that's performing badly. Then we have another well that's starting to perform poorly. We can easily start to see this context. It's a very space efficient. This is very similar to if you rolled this out, and let's say this was like a carpet that you rolled out, it could look like a bar chart, but a bar chart for many wells might take up a lot of space. This is actually space efficient, and it's not the same as a pie chart, because in a pie chart, your angles are actually changing for a different dimension that you're measuring. And those angles can be hard to interpret the difference of. In a rose chart, those angles are the same. And so this is really just a compact way of showing, again, like a bar chart.
Yeah, absolutely. This is also going to be used when you've got, say, data at a certain point in spatially and looking around that point in a 360-degree view. Like, say,
right.
For example, if you've got looking for wind speed at different wind directions from a location that's in the middle. So the rose chart, yeah, like Neil was saying, this is don't worry about the circularity of it. Like, there's issues when you're trying to discern sizes of in a pie chart of those slices, but in this case, the sizes are the same. You're just using this as a way of quickly in space efficient way, showing up variables that jump up over time in this case.
Couple more displays here. We have the Lollipop Visualization. So that's instant. This is shown on the bottom here. That's instantaneous. It's magnitude driven. It's easy for categorical comparison. We can see all these wells are performing well. And then we see a couple wells that are starting to perform poorly, or starting to have issues with their sensors, or the sensors are picking up issues with the equipment rather. And then a dot plot, this one. So I thought this one was interesting because what I'm doing here is actually taking the color, and when there's a recent value, that color is darker. And as that value becomes stale, the color fades out. And so you can actually use color to represent time here. And this dot plot is also using, this is using the X dimension to represent a measurement, but time is represented as a layer of color, and is changing at every second that is changing. So that's a dot plot, and that's has both instantaneous and historical values. So when you put this all together, it looks a little bit something like this. So this is a real-time dashboard. We have sliders in the top left that we can move, and then we can do a direct calculation on the real-time data stream. And that's actually can be used for conditional color formatting and change the data to represent the different thresholds that we have in those alert threshold sliders.
Awesome. I'm sorry to interrupt here. Just a few quick things. Dustin says this is one of the most amazing presentations he's ever seen in a while. So hats off for that. And
thanks, Dustin.
Thanks, Dustin.
A quick question here from Mike Nash. He's asking, do some audiences prefer different charts, or I guess are some charts better depending on the audience domain?
Yeah, to some extent, I'll take that. Neil can add to it. I think if you're just looking for a high-level dashboard, quick at a glance, keeping it really simple with line charts and bar charts, or just really quick inferential displays. And if you've got a more technical audience, you can start to get into some of the more details. And we purposely built up this presentation to get to that last slide Neil showed that has multiple visual tricks displayed with real-time data. So this is, more, you have to have a bit of a technical audience here. It's not, complicated really, but there's a lot of stuff going on here. You're moving sliders around to change the pressure and temperature gradients that you're getting from data directly from the pump. You're able to have that table there that's dynamically changing. You've got the curves building up over time on the right. So yeah, this one you'd want to make sure people understood how to read it.
Mm-hmm.
Yeah, and I would say also, data visualization, I believe, is both an art and a science, but what we're trying to talk about is the science of it, and where there's real objective advantages of showing one visualization to another visualization. So while certain audiences might prefer certain things, we are looking for a systematic approach to have better general human perception using a lot of research that's actually gone into how humans perceive objects in time and space. And we're using those principles to communicate data.
Awesome. Very, very interesting. I'm going to leave and let you guys continue.
Thank you. Thanks, so Dave. The final bit of this time section, we want to get into doing this display that's on the screen right now. You're really seeing, pressure, temperature, current, those things, accumulating over time, and you're putting sliders on them to look at thresholds, and you're not actually really doing calculations or predictions. You're displaying data, which is, awesome, but we can also do calculations on event stream data. So Neil, do you want to just walk us through both, static and real-time, calculations on the event stream?
Sure. So the event stream, so we can actually do calculations on both real-time and static data together, right? And why is that advantageous? Well, let's say that you are a F1 driver and you were trying to see how is your current lap doing compared to your best lap ever. Well, this is a little animation. Let me see here. Here's a little animation showing a car going around a track, and you're seeing this line represents the time that the difference from the best lap to the current lap. So what you're able to do by taking a real-time data stream and compare it to an at-rest data stream is take the historical context of something and then start making better decisions now based off of the knowledge you've acquired from the history. So how are things performing now? What is possible? What do we have built in the past? What do we know from the past? And how can we apply that to right now? So this is a direct calculation. This is happening at a row by row level. And it's elapsed time in two data sets compared in real time. That's what you're seeing in this little graphic here. There's two different tables being used in this calculation. It might be a little bit small in the view. Let me see if I can blow this up a little bit more. So that's what you're seeing right there, two different tables used in the calculation. Now that direct calculation, you can also have a direct row calculation that we're showing here. So this is just taking 4 different brake temperatures, 4 different tire temperatures, and it's doing a calculation to find the overall temperature of the tires and the brakes. There's different operators that can be used, such as conversion operators, date and time, math, text, utility. And these are, again, happening on a row by row level, also often called tuples when we're talking about real-time data. So this is happening on each individual measurement of data. But there's many applications for this which go a lot deeper, and this starts going into the predictive and prescriptive side of things. How can we actually have something prescribe to us what's going on? So for that, I'll hand it over to Michael to talk a little bit about some of the more advanced calculations.
Yeah, for sure. So this one here, that's the advanced part of this is really being able to detect the object and put a bounding box around it. And once you've got that, you've then got position data, and you can start to calculate things like velocity. So this is data that's coming off a video camera, tracking cars and trucks going by a certain fixed location. And we're using this idea of object detection to then do calculations. So you can see we've got a bounding box around the vehicles that is able to handle occlusion of one vehicle on another. And you can see down the bottom where we're calculating for each vehicle its velocity now that we're tracking it. So you get things like the time, the type of car, the velocity of the car, and you're able to start looking at how many vehicles are going by at a certain point in time and what is their average velocity versus the different type of vehicle, whether it's a truck or a car or whatever. So you're able to do those derived calculations. You're not actually predicting, you're still doing calculations, but you're able to then understand the traffic patterns in a fairly detailed way. Now, another way of doing calculations, and this one is a little more predictive and probabilistic, is predictive maintenance. So in this case, you want to look at the time in service on the x-axis and the cost on the y-axis, as that's the bottom right-hand graph here. And you're able to look at the different curves that are associated with the time in service. So, for example, the red curve on the lower right-hand side, that is the cost of doing a maintenance at a certain time interval. That is the predicted cost of an unplanned downtime. They're in the red. And so, you basically looking there at the failure probability as a function of time, and you're multiplying that by the cost of an unplanned downtime. Now, in the top right-hand corner, you're putting that into this table, the cost of an unplanned downtime, that's represented by that red curve. Now, you're getting that red curve by doing this reliability analysis on the left-hand side, where you're looking at fraction failing as a function of time in service on the left-hand side. And that gives you that cumulative probability of failure that you then multiply by the cost of an unplanned downtime to get that red curve. And that red curve is really where a lot of the money is and a lot of the expense is. Now, the green curve that's overlaid on that is the cost of maintenance. So if you do your maintenance too often, you get a high cost of the maintenance. If you don't do your maintenance very often at all, then the cost of that is low. So this is your cost of the actual maintenance repair, the green curve, as a function of time in service, and the red curve is the predicted expense of an unplanned downtime as a function of time in service. Now, when you put those two curves together, you get this blue curve in the middle, which gives you the optimal maintenance interval. So this one is a little more sophisticated in terms of the calculations because you're fitting a regression there. It's actually on the left-hand side, the regression that you're doing, fraction failing versus parts in time. It has a log scale on it. It's an exponential, it's actually 2-parameter exponential. It's a Weibull distribution that you're fitting. And so if you put that on a log scale, you can fit a straight line and get the intercept and the slope of the 2 parameters of the Weibull that you're estimating. And that gives you the curve that you're able to, that red curve, when you multiply that probability of failure as a function of time in service by the cost of an unplanned downtime, you get that red curve. And that's important in establishing that middle point there of the optimal maintenance interval. But the way the analysis we've got, on our community site allows you to plug in the cost of a maintenance and the cost of an unplanned failure, and to basically, get those two curves from the fit here. It looks like in the video we've got the actual fit done here, fraction failing versus over time on the bottom there, and you can see this cumulative distribution function for failure, and it's that cumulative curve on the top right that you multiply by the cost of the unplanned failure to get that red curve on the previous graph. So there's a bit of calculation going on here to estimate that fraction failing versus time and the cumulative probability of failure, and that's super important in getting that, multiplying that by the cost of that unplanned failure to get that cost curve that you're then able to optimize. So a few steps involved here, but this is right there on our community site, and you can plug in your data and see what your curve might be. And then finally, the anomaly detection piece. So in this case, it's pretty easy to look at anomalies or outliers in one dimension, but multiple dimensions gets a little trickier. And you can see from this chart on the top left, we've got the Y2 measurement, and you can see the red points here are, within the error bands of if you're looking at that Y2 measurement over time on the x-axis, you can see those red points are sort of within the range of variability. And then the lower right-hand chart is the Y1 measurement, and you can see also those red points are within the range of variability for Y1. But when you look at Y2 versus Y1 in the top right-hand corner, those red points are outliers. They're outliers in two-dimensional space, even though they're not outliers in the one-dimensional spaces. So we've, come up with a number of templates and analyses for being able to recognize automatically outliers in multiple dimensions. And if we just step through a couple of slides here. So this one here, we've got 9 dimensions. There's 9 different curves of data coming over time. And we can see towards the end there that 3 or 4 of those curves drop down. So we want to be able to detect that automatically, and it's a multivariate situation that we want to detect here, where those, if you look at those 9 variables at once, you'll see that last chunk of time there is different to the rest. The rest we're just kind of bouncing around the mean for each of those. Now, if you normalize these data so they're on a common scale, so you can see them like together like this. But let's go to the next slide, and you can see we're going to detect that little bit at the end there. That's different. Just pause a little bit on that previous slide, I guess.
Yeah, sorry.
So that little bit there at the end that I was pointing out is, that's the bit we want to detect, where the 3 or 4 series drop down compared to the other ones. Okay, so now we want to bring those data in, and we've got this, neural network model here that looks at those data, and it squashes down the data to a lower dimension compared to a higher dimension, in the functions, the logistic functions inside the neural network. You've got a high dimension version and a low dimension version, and the variables that are not reconstructed, the points that are not reconstructed very well from the lower dimension are the outliers. And so that you determine that by this thing called the reconstruction error of the higher dimension versus the lower dimension approximation, and that reconstruction error combines all the 9 variables into one. And now you can see versus time in that top chart there, where you've got an outlier with the points going above the threshold line here, and you can see what are out of the 9 variables, what is responsible for that particular outlier. So you've got your reconstruction error on the top that's showing the outliers, and then down the next chart you show the contributions of the different variables in predicting that. On the right-hand side, as you move your way down through the individual of the 9 variables, you can see how much each of those is contributing to that outlier on that particular point in time.
So
now,
here, like when we showed earlier that we had 2 dimensions right here, right? Well, when we expand that to a higher dimension space, when we have 9 dimensions and 12 dimensions, when we have many more, it becomes a lot harder to actually visualize. But that's what you're saying this is showing, right? These are the contributions of each of those individual dimensions to
exactly. Yeah. When you got 2 dimensions, you can show it on a chart, right? But when you've got 9, it's hard to show it. So we're just using that overall reconstruction error to show the outlierness of an individual point in time. And then we're seeing, what are the variables that are contributing to that outlier in that bar chart below.
Mm-hmm.
And now as you accumulate, outliers over time, you might want to find out if there are any patterns in those so that you can in real time understand when you get a new outlier, how is that going to be in the context of what you've noticed in the past. So we've got an analysis, I think, that clusters up. If you go to the next slide, there should be an analysis that clusters up the collection of outliers that you collect over time. And you can see now that we've fit a cluster analysis with, I think, 4 or so clusters, or you can just decide how many clusters you want to have. And in this case, we've got this particular cluster is showing a particular pressure reading in blue. That's important. This one's showing a pressure reading in green. That's important. And the other ones have, number of variables that are contributing to their cluster. So now we've got a bunch of different outliers that we've observed over time, and we're clustering them down now into these 4 groups so that you can quickly determine when a future outlier comes in, which type of outlier is it? Is it an outlier that's dominated by this blue differential pressure reading, cluster number 1, or is it an outlier dominated by this green reading, which is kind of cluster number 3, or is it an outlier that's got a number of different variables that are influencing it? And, if you know what your outlier type is, then you can deal with it and, to perform remedial action on that particular type. So we define these 4 types of outliers that we can now manage, quickly when they appear. So that's an example of how to analyze multi-dimensional data in time and find out when you've got something different to the usual, run-of-the-mill. So I think that's kind of what we wanted to show on the time data. We've kind of gradually built it up to real time and gradually built it up to multiple dimensions to show how we deal with ultimately multiple dimensions of data that are happening, in real time.
Yeah.
So we're going to move that.
I saw a question here.
Okay.
Yeah, I just wanted to pop this up. Someone was asking about the network chart that we have right here. Is that a custom visualization? Is that part of Spotfire? So Spotfire has Spotfire mods, and Spotfire mods are custom visualizations that are drag and droppable right into Spotfire. So you can download this network chart from our community, and then you just plug it into Spotfire. And there's a wealth of custom visualizations that you just plug and play that way. So that's what the network chart is doing.
Yeah, and it's real simple to manage those, and you can add them to your flyout on the left and just drag them onto your canvas just like any other Spotfire visual.
Yeah.
So yeah, I think the animated bubble chart we showed earlier is another example of that, but we've got a collection of these visual extensions to Spotfire that you can download and add to your flyout for your own use. Point and click, no code. There's code underneath it, but there's point and click for the user.
Right. All right, so our next section is on space, the final frontier in space. We wanted to follow some of the same format here. Let's talk about some basic principles when we're talking about spatial visualizations and visual displays. And then we'll actually then talk about spatial patterns, spatial operations, geospatial analytics, and applications. So, grab your coffee, buckle up. This is a whole nother section here where we have now gone over time, and we'll go over space. Feel free to ask your questions in the chat and let us know what you think of the session. But from there, let's go ahead and talk about some basic principles. So first, the benefits of spatial data. Spatial data and maps, geoanalytics, it improves your interpretability of size, shape, boundaries, density, proximity, and context. You're getting all of that from a spatial display. You're able to see the context of the river networks, the land, the water here. You're able to see the context of the road networks, the shape of certain boundaries, the proximity to each other, the proximity of these different housing units to each other. You're getting all of that, the shape of this bay, all of that from just one display. Now, spatial objects are used to construct spatial displays, and they really just boil down to three fundamental components. It's points, lines, and polygons. And points, lines, and polygons, you can make pretty much anything in a spatial display, including something like this floor plan map. And that's actually created with a shapefile. And a shapefile uses, it's actually an Esri proprietary format that's now widely used. And the shapefile uses points, lines, and polygons to make fully interactive displays like this airport floor plan. But when we talk about these displays and we talk about spatial displays, I think that can kind of lend a bias to thinking about maps and just geographic maps. And maps are not just geographic. So when you boil down a map, what is actually a map? And a map is a symbolic depiction emphasizing relationships between elements of some space, such as objects, regions, or themes. So it doesn't have to be geographical. It's really looking at the relationships between these objects, and it can come in many different formats. So let's talk about some different displays here. Now, the first is, of course, the geographical map. That's what we're most familiar with. This is a diagram representing land or water features, roads, cities, elevations. It comes in many different formats. You can have topographic maps that show elevation. You can have climatic maps that show atmosphere, economic maps that show resources. And it typically displays data relative to latitudes and longitudes. Typically, you'll have north pointing upwards. So the top of the map will be north. And so that's typically how a geographical map is. Now, when we're plotting data on a geographical map, we have map projections that are important, and that is how the points of your data wrap around and map to the surface of your map. And there's different projections here, and that would be important when you're actually using data analysis to map your points, to make sure you're using the right projection. And so when you look at some of these maps, you can see, like for instance, in Mercator, that the United States is actually the same size as Australia. But in many maps, some of these other maps, it might look like Australia is much bigger than the United States. So the different projections can distort what's actually happening on the sphere of the Earth. And that's why different projections are used for more clear representations, depending on what type of data you're showing. The coordinate reference systems are very similar, and that is also important. There's different standard coordinate reference systems. I'm sure there's like over 100 of them. I've seen dozens and dozens of them. And these are used to tell your data where on this projection and what coordinates they are. So the coordinates may not be exactly the same. And so you must use the right coordinate reference systems in your translation, your mapping. So a choropleth is a type of map, a geographical map. And this is an easy way to measure geographic data. It prevents the overlap of data. So whereas you might have point data where you have a bubble map and the points are overlapping each other, a choropleth is just using the geographic boundaries of a certain region, like states or a country. On the bottom right, we have unemployment rates during the COVID pandemic. This is by county. We're seeing those different regions. And the top left, we're using actually that velocity chart, the SuperSmoother, if you will, that we were talking about earlier. That is showing the rates of change of COVID cases across the world, and this can create distortions if it's not normalized correctly due to varied geographical boundaries. So you want to normalize your data when you're using a choropleth oftentimes. Now a cartogram, credit to Peter Shaw on our data science team who created the cartogram using the cartogram package in R. And he didn't invent the cartogram, but he did create these displays in Spotfire. And these are geographic boundaries are distorted to reflect a variable. So this is like you can see Texas and California, they're distorted to reflect COVID cases in these regions. And this actually reduces the bias you can get from geographic boundaries that are present in traditional choropleths. So by having the boundaries actually distort by the data itself, you're not like restricting the data you're not creating a bias of arbitrary boundaries where you might have Wyoming, for instance, which has, it's a pretty decent sized state, but it has a very low population. Because of that, it's actually having lower cases and it's becoming kind of crunched in the choropleth. Whereas California, Texas, and Florida and New York, those 4 states have high populations and high cases, so they're kind of blowing out. There's also, floor plan and building maps. We talked about this with the floor plan as, points, lines, and polygons can create the floor plan map. But this indicates resources and accessibility. It can be an arbitrary direction. You may not have north at the top of your map. It can be interactive as polygons for data analysis. And it's really just showing features of buildings and structures.
Yeah, and the top left-hand one is the San Francisco airport, and the bottom right-hand one is the Dartmouth campus.
Right.
To give you a feel for what's going on there. So the one in the top left has got really no geographic piece to it at all. It's just a layout of the airport, and the one in the bottom right actually does have a bit of geography in the background there with the campus. And yeah, if you look at that campus in more detail, we can actually blow it out into a tree map, which the location is non-physical in this case. These are buildings, and they're also rooms. And the color code is, the crowdedness of a particular room, in a particular building. So the big part of the tree map is the building, and then the little part of the tree map is in the room inside the building. And you see that red zone there in the left that shows for that particular building that it's in, that little bigger rectangle, that is a room that has, experienced quite a lot of crowding during the day. So we were, working with the university to figure out which rooms were crowded, which buildings were crowded, what's going on, on the campus at any point in time. Now, another display, next slide, is the heat map. So in this case, we're doing a heat map of admissions. The credit goes to Cliff Micah here at Baptist Health in Jacksonville, who has been running the operating facilities, rooms, and everything at the hospital with us with Spotfire. And so you see on the time of day is on the y-axis, and the date is on the x-axis. And then the color is in this case, the admissions coming into the hospital. And you see this hot spot in the morning. So it's actually in the afternoon, or the mornings and the afternoons, actually, at part of the peak, in last year, that you see a lot of admissions coming in. But the heat map here actually shows you time of day and day in this case, and allows you to communicate the hotspots via color. Now, the heat map can also be used in a bunch of other ways. In this case, we're looking at multivariate dimensions, and we're looking at correlations between the variables. And you can see we just highlighted the group in the top left-hand corner that has fairly high correlation amongst those variables. And we're able to display that, in this network chart. We're able to also filter down to just showing the highest correlations, so that being able to visualize the correlations in a heat map and understand relationships in a network chart allows you to figure out, contributes to what you would put into a model that you would use to predict in this case. So the heat map, does have a lot of utility for showing, relations, in this case, correlations. And then the network chart that's come up a few times here. Here's a display of opioid data and relationships between prescriptions and distribution of the medication as part of the opioid crisis. And you can see that the connections in the network here show those fairly complex connections between different parts of the supply chain, transactions and distribution between buyers and sellers quite effectively. And this is pretty big data that we're analyzing here with that network chart. So in summary, in addition to the geographic maps, the tree map, the heat map, and the network map are able to communicate interesting spatial data with different non-mapping type displays.
Yeah, I was gonna say it's about 18 million transactions that are shown in this network map, and in particular, like this last display and this display, these are transaction maps, so it's non-geographical at all, but it's still using the characteristics of space to display the information to create an interpretable display.
Yeah, exactly. So these are good companions to the geographic and non-geographic spatial analyses, to represent them in a tree map or a heat map or a network map to bring out the relationships in the data. But Neil, let's get back into some geospatial principles and bring it home here.
Yeah, so I wanted to talk about the data analysis side, and just quickly going over the different types of layers, different types of data layers that you might use in a geospatial analysis. So the first is a marker layer, and that's just going to be points. You might see these coming in different names, but we call it a marker layer. These points can be colored, they can be sized, they can be shaped differently. They can be transparent if they're overlapping a lot. So that's just your typical marker layer. A feature layer is a polygon or a line. So here, this is showing different neighborhoods and purple, different districts around. What this is really showing is Victoria, Australia, and showing the Melbourne area, actually, of Australia. and it's showing different housing prices and real estate prices, and we're seeing different neighborhoods and income in these purple regions outside there. Now, web layers can also be used. So live traffic can be pulled from the web. That can also create custom backgrounds as well. So custom background layers give the context and set the reference points for the type of data that you're showing. You should choose a background layer that really augments the data you have very well. If you're showing a lot of geological information, you might want to have a topographical map. If you're trying to show road networks, you want to make sure you're trying to show traffic conditions. You want to make sure the roads and the city boundaries and the state boundaries are all well shown on your map, things like that. And if you're geographic data, you really want to emphasize that you might want to choose a subtle background map that doesn't have too much going on, so that you can really emphasize the data itself. And then lastly, there's image layers. So in this Melbourne area, this is just a rectangle that's drawn in as an image to emphasize a certain area. You can also use an image as a diagram for context. So like if we have an injury map, you can see an image of a human in the background, and we're actually changing the coordinate reference system to map different data points and spatially put those onto the image background and get an idea of where the most injuries are happening for these workers. You can also use this as a background for, let's say, a seating chart, or even different types of charts like this ternary plot for geological features.
Terrific. So let's get through the spatial operations piece and showing different views on to communicate the spatial data.
Yeah, so there's many different spatial operations, and we can't cover them all, but they fall into some major categories like search, location analysis, distribution, measurement. We're going to talk about some of these today, such as like the Voronoi. We'll talk about corridor, buffer, patterns and dispersion and interpolation. So we'll talk about those today, but keep in mind there's lots of geos. We talked about the principles, the components of points, lines, and polygons. You have the ways those can be arranged to create different displays. Then you have now operations that you can do with those components to start getting into some analytics. So Michael, do you want to tell us a little bit about the spatial proximity operation?
Yeah, for sure. I mean, this is the idea. You want to have attributes of objects located in proximity of a certain location. So it could be like a store location, who's living nearby, what type of attributes on those people are, like income is often in the minds of retailers. And then you can look at that in both with respect to the proximity of a certain point, but also where do all the people with high income live. So if you run the video there, you'll see how we chose a particular point for a potential new store, and then who lives in the surround of that, in terms of their income. So you can see as I click around that store there, you can see the region around it. I'm going to highlight, and I can see the income distribution for that, for that region around that particular point. Whereas if I, go to a different point, I can go grab the coordinates for that and stick it into the field there, and I can look at, what is in that region, with respect to that income distribution. And then I can just look generally across the whole landscape and see, where people with different sort of incomes, live in general. So this, proximity analysis is useful for that, retail use case and many others. Kate has a question.
Yes. First of all, I love the interactivity and all the visuals in general. Just I love data visualization. So for me, this is like a kid watching their favorite cartoon. We had a question here from Herb, and he's asking, does the geospatial engine live in Spotfire, or is this an integration with a vendor such as ESRI?
No, it lives right inside of Spotfire. We can analyze Esri data, but the engine for our mapping is right inside of Spotfire.
I figured I'd say it wrong. So it's Esri. Okay, got it. Good to know.
No
Thanks.
No worries. So that's the spatial proximity type analysis. Now you can put buffers around your spatial locations. So in the next example, we can see that we've got a collection of wells. This is an energy sector example, and you can see the wells there in the lower right. but we've added a slider to look at the drainage around the wells. So this is useful to figure out if you're going to drill. You don't want to drill where the other wells have already been or where they're draining from. That's called a frac hit. You want to kind of avoid that. But in this case, we're putting a two-dimensional grid for the wells down to do the mapping, and then we're expanding that halo around the wells using a distance matrix calculation. So Neil, I think you're up next to show a little bit about how we bring out features from a map and use those to join and interpolate.
Right. So I want to talk about feature extraction now. We talked about points, lines, and polygons. Now, when you represent the spatial data, your data, you have to choose. Is your data represented as a point, a line, or a polygon? You can't have a data that's both a point and a line with the way your data is stored in rows. So one object is a line or a polygon. But if I want to take that line and I want to extract points, I have one row of data that is a line, and I want to extract multiple points out of that. Why might I want to do that? I might want to find the nearest neighbors to this line. Well, what's the nearest neighbor to a line? Well, there's points all along a line, right? I might want to do a spatial join to that line. I might want to do an interpolation of data points along that line. So why I might want to do that, for those different operations, and what I might want to do is then extract the points from it. So what this is doing is what the mouse is doing is it's clicking on a line. These are rivers. And when it clicks on that blue line, the R engine is running in the background. And this is kind of what Michael was talking about earlier with the interactivity with Spotfire. When you click on data, it actually triggers scripts. So it's a fully immersive experience. When I click on this line, it's going to generate all of these points. And the way it's working is it's extracting the vertices of the points, the vertices along the line. And when you have the vertices, then the distance between those vertices is a straight line. And so then you can just interpolate every 100 feet between that. What you end up with is basically converting a line into a granular set of points that you can then do these operations on. So one is a spatial join. And this spatial join is a distance matrix. Let me go ahead and play the video for you. So what we have here in these red dots are measuring stations. What you're seeing in these black dots are lines that have been converted into points. Those are rivers converted into a set of points. And then we have measuring stations. Well, the measuring station is going to be showing for pollutants that are in the area. And that might go to a set of different rivers. It's not going to just one river. So if I want to see all the rivers that are within a certain distance, I can join those points from one data set. I can join those river points to the measuring stations of another data set. The spatial join is a join using the context of two different data sets using a spatial characteristic to perform that join. And so here I can actually change that threshold. I'll play this video. You're seeing these measuring stations. You're seeing the black points. I'll move the slider, and that is actually going to connect more of these river points to measuring stations. And what that allows me to do is then say, hey, these measuring stations belong to these rivers. And then I can interpolate how does the pollutant actually travel throughout the river? How does the pollutant look as a gradient throughout the river? So rather than having just this very discrete limited data where I only have these entire lines and say, I can't say an entire line has X amount of pollutant. I can say at this location, there's X amount of pollutant, which is giving me a much better analysis. Now, next up is a intersection. And this is done by using two different polygons. What we have in green is a trade area. We'll talk about trade areas more in the analytics section, but the trade area is the direction that you can travel from a center point if you walk or drive a certain distance in any direction, right? So if I want to travel for 2 miles, I'm going to be limited by the roads and the bridges and the geographical boundaries around me. So that trade area is used to define certain cities in the Bay Area. It's a couple miles of distance around each of these different, Oakland. We have Fremont. We have different areas around the Bay Area. And then the blue is actually polygons that are showing census data. So if I want to find the intersection of where these cities are and what the census data looks like, then I can actually I'm going to play a little video here where I'm going to move these sliders for the census data. And as the census data comes off, we're starting to see these bars change. And this is for each city, showing the demographics of this city, showing the population and median income when I move different demographic sliders. So that's intersecting two different polygons, two different data sets.
So Neil, I think a lot of folks, there's some comments about a lot of information here, and they kind of need to absorb it. I'm wondering if we should sort of cut ahead and bring it home with the space-time combination, and maybe we can schedule another DATAcated for the more additional space analyses. What do you think?
Sure, yeah, we can jump ahead. We have some sections on spatial patterns, and I can skip through this, Michael, and we know that maybe do we want to talk about the geospatial analytics and the Voronoi, or do you want to just jump right?
I think we should just. I think we should just jump to the wrap up.
Okay.
Kate, is that okay with you? I think we're kind of like, I think people are starting to get brain overload.
Yeah, absolutely. I was going to say, while Neil looks for the slide, this is all being recorded. So for those who have to hop onto another call or get lunch or whatever, feel free to do so. This is being recorded. So up to you guys if you want to cover more now, if we want to do a dedicated session on talking about space as a standalone topic. Completely up to you, but this will be recorded and will stay on LinkedIn and on YouTube for viewing.
Okay. What do you think, Neil?
Yeah, I'd say let's do some geospatial analytics and then just wrap up with the space-time continuum. But there's some exciting stuff in the geospatial analytics.
Yeah, okay, that's fine. Yeah, let's do that. Let's get into the spatial Voronoi tessellations and things like that. What do you think?
Sure. And yeah, I mean, feel free to, for the audience, feel free to hop off and watch the recording later. We knew we had a lot of content coming in here, and we're very passionate about this content. So, feel free to jump in as you like. We'll probably go for another, I'd say 15 minutes and then be done at that point.
Okay.
So let me go ahead and show, here we go. So some geospatial analytics. Do you want to talk about the Voronoi tessellations, Michael?
Yeah, sure. So the idea of a Voronoi tessellation is that, all points inside of the individual polygon are closer to that polygon's seed or center point than they are to any other seed or center point. So you're basically putting these polygons around the individual points to create these regions of closeness to the individual centroid. Now that, when you've got analyses you're trying to do, we're going to show you some examples. That's a very useful thing. So in the energy sector, for example, next slide, you can look at, say, porosity, which is a good predictor of production of energy, hydrocarbons. And so here's your data on that porosity, and you're able to put the Voronoi analysis, the tessellations, to show these regions of different porosities across a landscape. Now that's useful in predicting production, and so these are the production well data that we've now layered on top of that. And the size of the point is the amount of production coming from a certain well. And you can see on the far left-hand side there's some high porosity regions and some high producing wells, that little group in there, right? So you can kind of see how the tessellation of the porosity is aligned up with the higher producing wells in that case. And you've got other patterns of the relationship between porosity and production that are occurring, say, on the top right, where you've got sort of low production and low porosity. So this tessellation, gives you the ability to show the surface or the groups of porosity across the landscape that allow you to understand production in this case. Now, another example of a Voronoi polygon here is kind of made up a little bit, but this is the idea of having, a group of, constituents that you want to make sure you can cover them, in this case, with a hypothetical clinic there in the orange dot. And so you can see if you want to put down 7 or 16 clinics, where would they be located to give you good coverage of the population that they want to serve? And you can, basically locate them with respect to a Voronoi tessellation as well.
Yeah, I think the key thing here, so the difference between the orange diamonds here and the orange diamonds in the other one is these orange diamonds are the centroid of the Voronoi tiles of this tessellations. And so each blue point is closest to the orange diamond in its tile. It's closer to that orange diamond than to any other orange diamond. It's closer to this centroid than any other centroid. And so this is evenly kind of, or not evenly, this is intelligently going through and actually distributing centroids and tiles so that not too many patients are going to one clinic, where at the same time, they're also not having to travel too far to get to a clinic. So you're not overloading the clinics and they're not having to travel too far. It's optimizing in those dimensions.
Yeah, now this is a bit of an approximation though, because it's like, this is kind of as the crow flies, which is not really the reality. So if you go to the next slide, you can see how we've constructed a trade area by actually looking at the drive time or the walk time from a particular point. And this factors in roads, walkways, bridges. It's more practically relevant than the sort of at the crow flies type of analysis. And so you can see here, as I'm picking a certain point there in blue, as I show the, well, I'm actually picking a new point here now in blue. And as I grab the coordinates for that and stick it in the box there, I'm now going to create a trade area of what is the driving distance from that point, who lands within this 3.9 or 4 mile driving distance. So this is, you can see now, as I've got that point, you can now see what is in that 3 mile driving distance in terms of places that I can go get a test or get a vaccine or whatever. This is shows you that spatial location that's accurate with respect to the actual driving on the roads. And you can see it's taking account of going over different bridges or whatever the case might be. But, this brings it practical reality around that distance in terms of the actual driving distance.
And I saw we had Mike Nash was asking, this would be perfect for calculating deliveries, or could imagine this would be perfect for calculating deliveries. Well, that's actually a really good segue into our next example, right, Michael?
Oh, yeah, exactly. Yeah. So in this case, we're doing a route optimization. And so there's a lot of different ways that you can do route optimization from, say, a distribution center to a store or delivery, like Mike was just saying. You can put on different capacity constraints about how many deliveries you have to get done in a certain period of time, or you can have this can be used for optimizing fleets or traveling salesmen or auditors who have to visit multiple places. The example we've chosen here is delivering fresh coffee to stores in the Bay Area, and we have a constraint on the maximum numbers of trips from each distribution center per day, and we want to minimize the total delivery driving distance. So this video is going to show there, and we're going to show the different numbers of distribution centers that are possible and the capacity constraint there. We're now putting in place so that the San Jose, which was going to be delivering more than it could actually deliver, it's now brought down that bit overlapping there, and those deliveries are being distributed around to the other distribution centers. And that's all in the name of minimizing the total delivery driving in the top right-hand corner. So we're minimizing that total delivery driving, but we're also allowing for a constraint of maximum number of deliveries from any particular distribution center to keep the coffee fresh, right? So this is a way of optimizing the routes and deliveries from the distribution centers to minimize the overall drive time while keeping the coffee fresh as it gets delivered to the individual stores. Yeah. So I think, we should maybe, bring it to a close, Neil, and come back and do a more specialized, advanced spatial section. I think that might be good.
Yeah, definitely.
Awesome. Just have one quick question here from Herb that I really liked. He's asking if Spotfire is able to assign latitude, longitude from addresses natively, or does this require an outside engine?
Well, we have a geocoding and reverse geocoding function. They connect to in order to look up the addresses, it uses a REST API. So you can use the TIBCO GeoAnalytics Builder, or you can use the Google API, developer API, and that's available for free in our community. So you can feed it addresses and get lat and longs back, or you can feed it lat and longs and get addresses back.
Okay, wonderful. This has been such an informative and...
Oh, I think we might have lost Kate for a second there.
Yeah. I think let's just wrap up the space-time continuum, Neil. And to do it justice, I'd like to come back and do some additional advanced spatial analytic topics in the future.
Yeah, we have plenty more content, so we can make another session. We'll have a follow-up, and it seems like people really enjoy this content. It was really good to see. Thank you all for joining. It was really great to see the interaction. And thank you,
Yes.
Kate, for having us.
Absolutely. It was a pleasure. And I'm going to briefly share my screen to do our last giveaway here. So I've actually started the drawing. I'm going to go ahead and share my screen. And let's see who the winner is. It already is slowing down. Congratulations to John Warona. I will follow up with you after the session. And again, Michael and Neil, thank you so much for being on the DATAcated show. I think you do have probably several hours of content left within you, but I understand.
Yeah, we didn't estimate our own running length as well as we might have, I guess. But no, the topics were pretty fascinating. We got a lot of good audience interaction. So I think coming back for the advanced spatial topic and bringing the space-time together would be another DATAcated session that we could schedule with you, Kate, if that's okay.
Yes, absolutely. Love to talk about that. And guys, everyone who's listening and watching the recording, go ahead and follow the TIBCO company page on LinkedIn. I know Neil has a great show. I shared a link there for YouTube, and follow them on Twitter. I will see everybody online. Thank you so much and have a great rest of your day.
Thanks, Kate. Thanks, everybody.